Okay, hi everyone. Welcome to machine learning. Today we're going to talk about variational autoencoders. Just make sure my chat is working. This looks good. Okay, so today we're going to talk about variational autoencoders, continuing our discussion on various ways of modeling and working with sort of complex data distribution models. So again, to place things in context, we've talked about a variety of models, starting all the way from clustering, and now talking about sort of density modeling. Last time we talked about generative adversarial networks as a way to build density models. Today we'll talk about variational autoencoders. This will use EM that we've covered a few times, so we'll see EM again, but in a somewhat more complicated way than the way we've seen EM over the past few lectures. So that's the rough target for the discussion today. So as mentioned, we'll talk about variational autoencoders. It will use a technique called variational EM, which is an extension of the standard expectation maximization. And based on this, we'll develop the tools. Reading material. The original variational autoencoder paper is by Kingma and Welling, so the reference is here. I think it's a reasonable read, so if you're interested, that's a good place to get started. And then there are some good tutorials out on variational encoders. It's by now a sort of well-studied topic. Okay, so a bit of notation, same as before. So we've been talking about density modeling over the past few lectures, really 1 or 2 lectures, where the explicit focus is I give you a data set and I want to come up with a model for that data set such that if I sample from my model, I can get data that looks like data that I would have gotten from that data set. So if you like, I have empirical data and I want to be able to sample sort of new data that looks like that data sample. So we want to do this using models as opposed to just subsampling on the original data, because we want to generate completely new samples, so including samples that we haven't seen before. This again was, if you remember from last lecture, talking about GANs. We wanted to do this for GANs because we saw that GANs did a good job of being able to synthesize, say, new faces and new X-rays that were very different from anything that we've seen in the existing data set, which has lots of, I think, interesting applications down the road. Okay, so there are many ways to do this. The simplest way is if you think that a parametric distribution does a good job fitting your data, then you can do what we've done over last week and week before. You could solve maximum likelihood and set the parameters of that empirical parametric distribution. So we talked about, for instance, doing this for Gaussians, mixtures of Gaussians, hidden Markov models for sequential data, where the target is to fit the parameters of some parametric generative model. So it's a model where all the distribution steps are well specified. And we thought about this in this sort of graphical model sense, where we drew variables and arrows. So if you remember, let's see. So for graphical models, we drew sort of variables and arrows. The simplest one was when we're thinking about hidden, like clustering models and the like, where we had a latent variable and observed data sets. And we thought of it in this sort of structured, synthesized, synthetic generative model form. You might also remember that we extended this, for instance, if I allow this to be in a chain, then I get something like the hidden Markov model. So a bit of a recap, C3, and so forth. And of course, you can make this interesting and as complicated as you like. As I mentioned last time, there are entire courses thinking about how to construct and fit complicated graphical models. We'll stop here in terms of thinking about parametric graphical models, but to mention that there's a whole sort of additional literature that if anyone's interested in following up. Okay, so you can fit the parameters of a parametric distribution. You can fit parameters of a more complex parametric distribution like mixtures. You can use kernel density estimators. We spent a bit of time talking about these, which are sort of simplified models that explain complex distributions by doing little bumps around simple distributions. Feel free to look in previous slides for this. We looked at adversarial methods in the last lecture. So we thought about GANs as the canonical example, generative adversarial networks. And the idea was that we're going to fit the generative model by finding a model that does a good job minimizing some adversarial loss. And so the goal of synthesis is thought of as a two-player game. The generator is trying to create new data. The discriminator or critic is trying to tell whether the synthesized data is real or fake. And the target then is to come up with a model that does a good job of synthesizing data such that it fools the discriminator. And we train this, nominally, there should be implicit optimization function where it's sort of an outer optimization over minimization over critics. This is hard to train, so we use an alternating method, just like we did in earlier work, where we fix the critic or adversary or the discriminator, and then update the generator, fix the generator, update the discriminator, and do this back and forth to convergence. We also had a different interpretation of this as a divergence and minimization problem. Okay. As mentioned, we did this a bit last time, but I'll highlight it even more. We're going to modify notation a little bit to focus more on parameters, because particularly for variational autoencoders, they use maximum likelihood semantics. And so thinking about things in terms of parameters will end up being useful. Okay, so one way to reason about variational autoencoders, that's a little bit different. And at the end of this, we'll talk about how it's different from a GAN model, purely in terms of the synthesizer. Now we'll talk about how to fit these models later. But in terms of what the generative structure looks like, one way to reason about what variational autoencoders are assuming is something known as the manifold hypothesis. And the idea is that observed high-dimensional data is actually sort of has low-dimensional structure that's embedded in the high-dimensional space. So there exists some low-dimensional, potentially complex objects, such that if I could figure out what the subject was, this would be a good explanation for the data generative model. So in pictures, here's an example where the underlying, in this case, we'll call a manifold, would be this curve. And this is two-dimensional space, not high-dimensional, but the idea here is that the observed data is really, even though it looks two-dimensional, it's actually generated, and here it's literally generated from a one-dimensional curve, where all the data are sort of sample a point along this one-dimensional curve, potentially parameterized by Z, and then sample data based on some simple model around the point that you sampled from the one-dimensional curve. So in particular, I say I sample a point here as an example. This point might be equivalent to that point along the one-dimensional curve. And then I sample data as sort of some point with a bit of, here in this example, you can think of data as the mean is equal to the actual value on the curve, and then maybe a bit of extra noise around it. So explicitly here, my data sample is a function of the underlying original latent variable, pushed through some mean function with some additional noise. And this fully describes the observed data. And in these kinds of models, the mean function is generally a deep neural network. There's a good question in the chat I'll answer in a second. But in principle, you could make these lots of different things. So there's a question about what's the difference in a subspace and a manifold. So the main difference is linearity. So generally, when we talk about subspaces, we're thinking of linear, I want to say linear manifolds, but that sounds unreasonable. But these are linear lower dimensional spaces. So in particular, in a two-dimensional space, since D is equal to 2, the only way to go lower dimensional is to have a one-dimensional space. So the only option for a subspace in the two-dimensional space is some kind of line So in particular, you might imagine then, let's pick a different color. If I wanted to do a subspace, I might have a subspace that looks like this. And so the only kinds of models that I can explain as a subspace in this setting would be models where the observed data is sampled close to a line. So you can have the same exact model, but my samples are sort of points close to a line, which is, again, the same model, but this mean function might be a line, something like W transpose Z. So the difference is that for manifolds, we allow nonlinear. There are restrictions. Typically, there are sort of rough smoothness assumptions that are made. Usually, we assume that they're connected, though they don't have to be, meaning sort of all parts of the curve can be reached from all others. It's more a vague notion in most of machine learning than sort of very explicit in terms of mathematical definition. There is a mathematical definition of a manifold, which is somewhat more precise than what I'm describing. This is on purpose because there are many data structures that we think can be expressed as manifolds, but maybe not completely exactly. So one good example of this is if I look at images, but I measure them from different locations. So what I mean specifically is say a 3D object, and what's the view of the camera of myself, my face, for instance, or my head, which is a 3D object. And so in this setting, the camera is giving a two-dimensional projection of the 3D object. You can imagine that if I looked at all possible measurement locations, so if I move the camera everywhere, it's measuring the same objects. So the actual degrees of freedom are not the space of images of my head. The actual degrees of freedom are just the angle of measurement. And so one could imagine drawing a three-dimensional manifold in camera space that fully explains all the different images you can get of someone's head. So these are some of the intuitions that drive thinking about complex data as manifolds. This comes up not just in images, though I think images are the most intuitive and clear place where we think of data as coming from a manifold. But you can also think of this in sort of other applications. Mostly it's capturing the idea of low dimensional structure. So there's a question in chat about what is Z doing. So Z is capturing, quote unquote, the true degrees of freedom in your data. So the low dimensional degrees of freedom. And the idea is that these low dimensional degrees of freedom are expressed in high dimensional space by being mapped through some function. So there's some function, in this case, our neural network function that maps low dimensional degrees of freedom, in this case, one dimensional, but you can imagine, I just give an example of 3 dimensions. Or you can do higher dimensions, as we'll explain in a few minutes. But again, I have low dimensional structure, but high dimensional data. I want to explain what's going on in the high dimensional data with some probabilistic model. And one good way to do this is, in many cases, you can either argue or show, or actually prove in some more restricted set of cases that the underlying data is well explained by low dimensional degrees of freedom. And this Z is exactly capturing the low dimensional degrees of freedom. So there are a bunch of names for it, but you should think about it here as the sort of underlying degrees of freedom in the high dimensional data. Does that answer the chat question, both of those, the manifold and what's going on in Z? I'm happy to expand a little bit. Okay, so it seems like that sort of answers those questions. Okay, maybe a good question just to check that folks are following. How does this differ? If I wanted to write a GAN with a similar kind of intuition, what's the difference from the GAN generative model from what I just described as the VAE generative model? What's the difference between the two? So there's a not super subtle. It ends up being important actually, but there's a key difference between both models. How a GAN would model this this observed data, and how this generative model I just described, which we'll set up as the variational autoencoder. Yes, so the GAN has a very similar structure. Both fit high dimensional data. And the difference here is actually just really it's one thing. It's not about both will use high dimensional data directly. We'll talk about, for now I'm ignoring the fitting procedure. There's actually additional differences in how I fit the models that are super important, but we'll spend time on that later. But even in the purely in the generative model, there's a key difference between what the VAEs do as described so far and what the GANs do. So the GANs and VAEs share implicit models. Good comment so far, but both of them are trying to model high dimensional space using low dimensional Z. The GAN does this, again, using a neural network. This is what the generator is doing. Generator takes a low dimensional Z, maps it to a high dimensional space. If you remember from examples last time, the VAE also does the same thing. So the difference is that the GAN and VAE differ in the noise. So the GAN doesn't have observed noise or high dimensional. So the GAN model assumes that the observed data is exactly explained by the generative neural network. So Z going through the neural network G fully explains the observed data X, whereas the VAE assumes that the forward model, the implicit model, only explains the mean of the observed data. And there's an additional observed noise that you add on top of the mean. So it's a bit of a subtle difference. It turns out to be quite important in practice and in fitting models. Again, the difference is the VAE adds this observed or high dimensional noise. The GAN doesn't assume, the standard GAN model doesn't assume high dimensional noise. We'll spend a bit of time thinking about some of the implications of this later on. Okay, I'm messing up on moving slides. Any, assuming no questions, we'll move forward. Okay, oh, right. Okay. Hope I kept those annotations. Yeah, somehow that's a different slide. Okay, so now we're going to think about expectation maximization as trying to fit this kind of model. If you remember, we argued that we can't do it in the GAN case, and I'll explain in a second. We explained in the GAN slides why that's a problem. I'll expand a little bit as we go forward why that's a problem for GANs. It's still challenging for variational autoencoders. And part of the discussion will be talking about a quote unquote trick that you can use to actually make the problem tractable. So to recap where we are trying to come up with models for high dimensional data. We've made the manifold assumption. We've said that this high dimensional data is explained by some low dimensional distribution pushed through some neural network. And this explains what we observe in high dimensions with or without noise, depending on exactly how we're sort of constructing the model. And what we're now walking through is how to fit the parameters of this model. In the last lecture, we talked about using adversarial losses to do this. Now we're going to talk about using expectation, fitting it using maximum likelihood, and specifically using expectation maximization, like we've already covered, but now sort of a special version of it. Okay, so just like we covered when we're doing both clustering models and hidden Markov models and sort of all the models of that like, we assume that there is some hidden variable. Again, this hidden variable is the latent degrees of freedom. And we're looking to estimate the parameters. Okay, so we're looking to estimate the parameters. And in this case, we're going to apply our favorite trick. So we're looking to estimate data. We're going to apply our favorite trick. Our favorite trick is maximum likelihood, which is max, forgetting to switch, max over theta, P of theta of X of the observed data. And if there are multiple observed data points, as you remember, we typically assume, or sometimes we'll assume IID. We'll ignore this for now because we're using latent variable models where not everything is IID. But okay, so this is a task that we want to solve. And our model happens to have this latent variable structure. So our parameter or our distribution of data is actually sort of a marginal if I integrate out some latent variable z, which is this unobserved data, which if I knew it would explain how x is generated. So if you recall, just to recap again, our generative model here is z is explaining x. And earlier we did simple things. We're going to do more complex things now. In particular, we're going to allow z to be continuous. And we'll make this mapping a deep neural network. So that's where we're sort of going in 2 seconds. And we want to fit this using maximum likelihood. So as you might imagine, this will be more challenging than what we've done in the past. Okay, so we want to solve this in maximum likelihood. As explained before, we generally use log likelihood instead of regular likelihood. Again, we've argued why this is okay and often preferred. So we're going to solve this using EM. So we talked about EM last time. In the E step, we find the distribution that maximizes this lower bound. We find the best answer. Based on this best answer, we solve a maximization problem of this lower bound. And the key step here is that in order to maximize this lower bound, the M step, we need this parameter. So we need the distribution of the latent variable given data. And so in order to do this, we need to solve the E step. So in the E step, we compute this distribution. In the M step, we maximize based on expectation over this distribution. Again, good to refresh your memory over the past few slides. The key important step here is, if you remember both from homework and over the past few lectures, we've shown at least a couple of times that if I solve the E step, you could show that the best answer, so the choice of Q, we used to call this A theta in the discrete case, but the choice of Q, which is the distribution over latent variables given data, that does the best job of maximizing the lower bound, is the Q that's equal to the actual real conditional distribution. So the best Q you can pick is the conditional distribution. And so we'll start from there and try to build on this over the next few minutes. This is a good time for questions. This is, I know we're covering some somewhat conceptual, tricky material. It's going to get a little bit trickier for at least a couple of slides. So if there are questions on the construction, this is a good time to ask. So far what I've discussed or recapped is how one describes what the EM problem is and how one tries to solve it. And in a couple of minutes, we'll talk about the variational version of EM, which is will allow you to solve the problem. Where we're going is in cases where we can't solve this step exactly. So the E step is hard to solve, harder than what we've seen so far. Any sort of recap questions before we move forward? Okay, so the question is, what's the relationship between Z and Q? So Z is a random variable. It's a good question. So Z is a random variable. In this case, Z is the latent variable. And what we want in the E step is to find a good distribution for this latent variable. So we're asking, what is the distribution for this latent variable that maximizes this loss function? So just again, we're maximizing loss functions. We're optimizing loss functions everywhere. Again, as I think someone mentioned very early in the class, a lot of machine learning is optimization. So we've come up with a version of maximum likelihood where in order to solve maximum likelihood, we need to maximize a certain loss function over possible distributions. So Q's are different choices of distributions and want to get the best one. To give an analogy to maybe something that hopefully makes this a bit more tractable, if you remember in our clustering lecture, instead of using Q, we're using A. We did this on purpose because we were thinking about soft clustering, and A was meant to capture all the different ways that I can assign weights to different clusters for a particular data point. And so finding the best A meant finding the best cluster assignments, probabilities. It's the same exact thing beyond the discrete setting. So if I'm no longer looking at discrete problems, then my probabilities are no longer vectors. They're now functions. Meaning if I give you a Z, I have a sort of score for the density of Z given data. And so the optimization problem we need to find is still the same. We need to find the best distribution. And we're going to, what we said in the past was this solution has a unique solution. Sorry, this problem has a unique solution. Again, in class, we showed that you can find this unique solution. That we ended up with a bit of Lagrangian because we wanted to make sure that this distribution summed to 1. You've done something similar in your homework. Q is capturing this distribution of Z given X. It's searching over different choices of distributions to get the best one. So Q is, each Q is a choice of distribution. So Q of Z are different choices, distributions, possible distributions for the E step. And the solution is the best distribution under this loss function is exactly the conditional distribution. That's exactly true. And so, okay, so hopefully that clears things up. And where we're going is in the case where finding this conditional distribution is not an option and we need to do something else. So Q is just a variable representing all possible E step options and want to pick the best one. And we know in the general case that the best one is the conditional distribution. So P of Z given X, and we'll expand on this in a second. So yeah, from the response, I imagine that this is a bit clearer. So, okay, so I'm gonna move forward. So we're gonna do this with neural network functions. So again, I have a two-step process. I have Z from some simple distribution like a Gaussian, and then data given Z, where the mean is some neural network function, and then I have additive noise on top of that. So it turns out, I mean, it's maybe obvious, this is true for all the cases where we've used EM so far, that direct maximum likelihood doesn't work, so we're gonna try and use EM. So again, in the E step, we're gonna try and find this P of Z given X, because that's the best Q, that's the best choice of distribution. And if you remember from class, the way that you find this best distribution, we've shown this a few different ways, but again, this is the joint P of Z X divided by P of X. So that's just definition. Unfortunately, this joint requires P of X. P of X it requires an expectation. It turns out that this is an intractable problem. So this integral is something you need to compute in order to find P of Z given X. Because I need to know if I integrate over all possible choices of Z, which is again this latent variable, degrees of freedom, I need to know what the integration, so what the average over all these choices are, average with respect to P of X given Z. This problem is a high dimensional integration problem. This problem turns out to be computationally intractable. Like we just don't know how to solve it efficiently for any kind of intrinsic problem. So we can try to hack it. You can try to sample. So push sample Z, sample X given Z, sample a lot of these and use that as a Monte Carlo approximation of this integral. This turns out to be very expensive and not tractable for what we're trying to use. So it's not efficient. We're gonna propose an alternative approach where instead of getting the real posterior distribution, we're going to construct an approximation. And our optimization problem now would be to find a good approximation of P of Z given X and use that approximation for our E step. So to recap, we want to solve the EM problem for complex models that include neural networks. The E step is intractable because it requires a normalization factor that requires a high dimensional integration that nobody knows how to compute efficiently. So what we're going to do instead is, instead of trying to actually come up with ways of computing this integration, we instead are going to come up with an alternative approach that replaces the real conditional distribution P of Z given X with some other proxy. And the job then is, what is a good proxy? So that's what we're going to cover in a couple of minutes. So we find a good proxy for P of Z given X, and we use that for EM. So now the new alternating optimization is, in the E step, we'll find a good proxy for P of Z given X. In the M step, we'll update the parameters, and we'll do this alternately till we get to a solution. Okay, so if there are questions, feel free to ask. So again, this is where we're going in terms of the setup. Okay, so this has a name. This is called variational EM. It's called variational for mathematical reasons that we won't spend a ton of time on. But if you thought of sort of variational approximations, it comes from variational approximation in functional analysis. So the roots are a bit complex. Those details are not important for our discussion. What's important for our discussion is just the name. So we'll call this variational EM for now, for the rest of this discussion. Okay, so the next question you might ask is, well, what should I use as this approximate choice of P of Z given X? So what should I use? P of Z given X is called the posterior, as some of you might know. If you haven't, we'll just mention it now. And this comes from sort of Bayesian roots of some of this work. So just think of the posterior as P of Z given X. That's all that's important for this conversation. Okay, so this is what we want. This is not computable, it's intractable. So we're going to approximate it somehow. And so a reasonable question to ask is, what is a good approximation? And so the claim is that a good approximation is, well, let's just build in our neural network and use that neural network to construct a density model and use that density model as an approximation. That's exactly what the VAE does. So what the VAE does is it says, I'm going to restrict my search for P of Z given X to only functions that can be described as a Gaussian, but the mean is a function of the data and the covariance is a function of the data. So you can see this a bunch of different ways. One way to see it in terms of the forward model of the neural network is that if you think of the sampling process, what I want to be able to do is take X, original data, push it through a neural network and get two quantities. I'm going to get a mean function. So this is given a certain data point, I want a function, a mean function and a covariance function such that they fully describe my Gaussian distribution for sampling Z. So this gives me a density model. And just as is brought up in the chats, where we're going is we're going to end up with this huge neural network, just like before, actually, with GANs. So we're going to have two neural networks, one that's sort of doing the generation part and one that's doing some kind of scoring. And we'll do a sort of end-to-end gradient descent over the whole thing and solve this using alternating minimization. So a lot of the semantics between GANs and VAEs are very similar. So as mentioned in the chat, we're going to just have sort of a big stack of neural networks that we're going to fit using stochastic gradient descent. The differences, as we'll get to, are in GANs, we're doing this in order to minimize some divergence measure. In VAEs, we're doing this in order to solve maximum likelihood. So the goal and the role that the two neural networks play are very different, but the sort of architectures are actually quite similar. In most cases, we have a generator that's trying to synthesize data, and then we have some other neural network that's trying to help fit the model. So yes, it's a good question or good comment. Okay, so why do we use a Gaussian distribution here? That's a great question. Historical reasons and tractability. Gaussians are really convenient for lots of computations because things simplify. There's a lot of sort of current work trying to expand and use more complicated distributions because there are cases where it can be helpful. In most applications, you can get away fine with a Gaussian distribution. So it's very similar to sort of in the beginning when we're talking about OLS, why use a Gaussian model or why use squared loss. The nominal answer is it works well in practice. But then you can also give additional answers, maybe based on law of large numbers or sort of other either theoretical or empirical concerns. I think the nominal answer and closest to the truth is it works well. well enough, and it's sort of easy enough to fit into how we do computation. Other kinds of models will shoot up the complexity non-trivially quite quickly. Gaussians will actually work out the details of this Gaussian model, and hopefully you'll see it actually works out reasonably easily to using a Gaussian model here. So in terms of the computation, it's also understandable, reasonably straightforward. Okay, good question. Okay, so sometimes you see this written as a probabilistic encoder. The idea of an encoder is something that takes real data and turns it into sort of low-dimensional representation. So sometimes you'll see this posterior model called a probabilistic encoder, because you can think about it as taking the real data distribution and mapping it down to a low-dimensional data distribution. There's a question about, do we have the softmax layer at the end to have a value of z? So this is not a, we'll talk in a bit more detail. This is not sort of, this part is standard neural network. It's a really good question. So this is a deep neural network. And this part, so I'm cheating a bit, and I'll explain the cheating in 2 seconds. This is sampling. Because if you look at this model, what you have are mean functions and variance functions, and then z is a distribution parameterized by the mean and variance functions. So really what this neural network gives you is the distribution, and the actual z is a random variable drawn from this distribution. So so it's precursor to answering your question. So in particular, the neural network itself would have layers that make sense for the problem. So for instance, it makes sense to do softmax or something else that forces positivity for the variance term often. The log variance, I guess, is not that restricted. You might have other kind of restrictions. If your data is all positive, then maybe you have restrictions on the mean and things like that. Yeah, so the layer question is not super relevant right now, but I'll talk about stuff in detail as we move forward. Why don't we directly derive z from the hidden layer? Why do we explicitly derive Gaussian parameters? That's a great question. So the reason that we fit the model this way is because we're trying to solve the maximum likelihood problem. And what the maximum likelihood problem needs is an approximation of P of z given x. So this is the goal. This line is the exact goal of the problem that we're trying to solve. And so all of the machinery is in service of solving this problem of how do you approximate the E step. If you wanted to use a different technique that involved directly estimating z, I think that's completely fine. There are techniques that look like this. If we don't cover it in this class, but there's a whole literature on autoencoders where you directly map x to z and z back to x, and they have their place and they do lots of interesting things. You can think about them as nonlinear extensions of PCA. So PCA, as you might recall, is a way to map high-dimensional data through a linear manifold or a subspace to low-dimensional representation in a linear way. You can do a nonlinear version of PCA, and these are typically called autoencoders, and those map directly x to z, z back to x. In this setting, our goal is to approximate EM. That's where we're targeting. And to approximate EM, we need an approximation of the E step. And in order to approximate the E step, we're going to do this so in order to solve this problem, we actually do need the sort of neural network parameterization of the distribution, because what we need is the distribution for the sort of EM, the E part of the EM. So hopefully that answers that last question. Cool, good question. All right, so putting things together and cheating non-trivially. So the parts that are sort of well-defined neural networks that don't involve sampling is, so let me just quickly draw a pen. So sort of up to here, and so this is a real deep neural network. This part, maybe with a different color, is sampling. So this parameterizes a model where we sample. Based on the sample, I have another real neural network, which is conditioned on Z, fits the parameters of the data, which is another deep neural network. And then again, there's a sampling step at this end, which tells us how to sample data given the parameters. Okay, so this is a cartoon to hopefully simplify how things are connected. And we're gonna backprop through the whole thing, which is where we're going. But the key steps, which is gonna end up being important actually down the road, is that there are these sampling blocks in the middle of our deep neural network architecture. This has turned out to make some things tricky, which we'll try to solve as we go across. Okay. So again, this Q of Z is sometimes called a probabilistic encoder. It maps X to Z, but it does it via distribution. So it specifically tries to model Q of Z given X. So it's an approximation of what we really want, which is the real P of Z given X, but it ends up being intractable. So we're going to try and approximate it. And then P of X given Z is often called a probabilistic decoder. So this guy, we think about it as a decoder because it takes a latent code, low dimensional representation, pushes it up to something in full dimensional data space. And it does it probabilistically. So it's, again, capturing the parameters of a distribution. It turns out to be much simpler because it only really it defines the mean function and then there's additive noise, which is why often we can just think about it almost directly as X. But that's the next few slides will be talking about how we actually try to fit a model that looks like this. Okay, so together, sometimes called this a probabilistic autoencoder in comparison to a standard autoencoder. And we're going to train this using variational EM, where in the E step, we can't really compute P of Z given X. We're going to approximate it. In the M step, we'll update parameters based on our fake E of Z, P of Z given X, specifically this distribution model. Okay, so we're going to work through how to do this. Sorry, I keep forgetting I have extra comments. So one more comment, the whole thing will end up being fully differentiable. So we're going to use sort of forward, backward passes, just like we learned when we learned about neural networks. So the whole thing we'll learn via backpropagation and stochastic variational, stochastic gradient descent. Okay. So in order to describe how to solve the E step and what we're doing, it's good to take another look at EM. So we'll again expand on the EM problem in order to sort of both explain and justify what we're doing when we try to find this approximation. Okay, so as you recall, as I'm mentioning now, so we're interested in maximizing the log likelihood. Since we're using a continuous distribution, not a discrete one, this maximization of log likelihood, this is not accurate. This should have, oh, sorry. So what I'm going to do over the next few slides is to rederive the EM. Yeah, there should be a DZ, which is what I was missing. There's also some other details, but I think the DZ is the important one. We'll skip this everywhere. So, but anyways, I think we should try to be as precise as possible. So let's go ahead and just add it in. Okay, so we're interested in optimizing this. So we're going to try and derive EM from first principles just because. And we'd again just justify the E step. So what I'm going to do is replace this log probability with a product with Q of Z given X. This is a density. This integration will always integrate to 1. This term doesn't depend on Z. On Z, so hopefully you can see that the left and the right-hand side are exactly equal. Okay, so all I've done is I've taken something, I multiplied it by 1, where 1 is equal to integration over Z Q of phi of Z given X dz. Okay. So as this is a density, by definition, it integrates to 1, so I multiplied by 1. Okay, so let's expand a bit on this. So what we're going to do is now add in or rewrite this via a ratio. All I've done here is write my P of X as the joint divided by the conditional. So this is all this is doing is, as you remember, P of Z given X is equal to P of XZ over P of X. I can swap the two. And so that means P of X is equal to P of XZ divided by the conditional. So hopefully that's clear. That's step number one. Here. Step number two, I'm going to then multiply and divide by 1. So the multiply and divide by 1 is Q of Z given X. Let me highlight it instead. Sorry, I'm multiplying and dividing by the same quantity, so it doesn't change my equation. However, I can split this up. So this gives me 2 terms. So what I'm doing is I'm looking at the log of the product. The log of the product is equal to the sum of the logs. So this first term becomes here, and this second term comes from there. Okay. And what is interesting and nice about this decomposition is that it allows you to write the log likelihood as a sum of 2 terms. We didn't do this earlier, but it's exactly equal to the sort of, and the last time when we derived this lower bound, we just sort of stated it and then worked through why it's a valid lower bound. You can think of what we're doing now as deriving it from first principles. It turns out to be useful for this problem. And so you can write down this, the log likelihood as a sum of 2 terms. One term is exactly equal to what we wrote as this lower bound L bar. And the other term is exactly equal to KL divergence between an approximation distribution Q theta and P of Z given X. Okay. So I've written this log likelihood as a sum of 2 terms, one term being a lower bound, the other term being the scale divergence. Okay. Some things to, I guess, point out, which will end up being useful, is DKL of any KL divergence is always positive and is only zero if the 2 terms are. So if I do this between A and B, DKL AB is equal to 0 if and only if A is equal to B. So it's only 0 if the 2 distributions are exactly the same. Okay, so just based on the fact that it's non-negative, it immediately shows the lower bound. And so this is one way to derive that the log likelihood is lower bounded by this LQ term that we derived a few lectures ago. So what we've done, to summarize, is we're deriving the lower bound once again, but now from first principles. Questions so far? It's a little bit, hopefully I've outlined all the steps so you can do it yourself later. It's one where I think it's useful to work through on your own just to make sure that you understand all the steps. So it's a bunch of sort of simple manipulations that we've used in order to construct this lower bound. Okay, so this L bar has a name. We haven't called it this name yet because we weren't using it very heavily, but it's often called the evidence lower bound. You'll often see this written as elbow. Also, notation-wise, you'll often see this written as a script L. This is important because, again, we have to play this game of compiling notation across lots of problems, and this ends up being messy. But if you read papers, you'll most often see this lower bound written as a script L as opposed to L bar. So a pointer there. Another maybe obvious point, which is very clear when you look at this function. So this is one nice thing about this derivation is that when these terms are equal, the KL term is equal to 0, which means that the left-hand side and the right-hand side are exactly equal to each other, which is one way to see that this log likelihood is exactly equal to the lower bound when I set my Q theta equals to P of Z given X. So when my Q is equal to the P of Z given X, to the true posterior, the KL term goes to 0. Since this log likelihood is equal to the lower bound plus the KL term, it must mean that this log likelihood is exactly equal to the KL term. So the lower bound is exactly equal to the log likelihood. We used this before, if you remember. We used this in order to show that optimizing the lower bound always improves the likelihood. So we drew this figure. So if you guys might remember, where we sort of had these sequence of lower bounds and we're improving it. It's the same exact idea here. So in particular, when I set my Q equals to P of Z given X, I get exactly the same left and right hand side. What is the range of KL and when does it achieve its highest value? So the KL divergence is a sort of distance measure. It's smallest when the two distributions are the same. It's largest when the two distributions are disjoint. So when the easiest example of this is sort of, suppose I have distribution 1 here and distribution 2 that's here. I'm going to use a different color. And I will intentionally try to make this disjoint. Say this is distribution 2. So if I have two distributions that are disjoint, I'm going to have trouble in the log if you work this through. The KL term has this log term. If I have disjoint distributions, I end up with a log of 0. Log of 0 will give me negative infinity. And if I work things through, I'm going to end up with an infinity term. So the largest value is infinity when you have disjoint distributions, and the smallest value is 0. To answer that last question, probably spent too much time on that. Anyways, so 0 to infinity, infinity happens when any two distributions are disjoint. And so we're looking for a Q that gets us as close to 0 as possible. We know the actual 0 point in theory or conceptually, but it's not computable because we can't actually compute this term. So we need some approximation. And so we're going to do this approximation using optimization, essentially. So we're going to do gradient descent on this loss function as a way to solve this optimization. Okay. Any questions on this? It's an important slide. Any other questions, I guess? Okay, so let's move forward. So, so you can think of this lower bound as a regularized loss function for the parameters. In fact, you can expand it itself. I'm not going to do it because of time, but if you expand it, you'll end up seeing that this lower bound itself can be written as a sum of a KL term, which is what this expansion is showing. So we want this, plus this expected likelihood term over Q of X given Z. So you can interpret this as a regularized loss function, and it's often interpreted this way. You can think of, and we'll show, that this first term you can interpret as a reconstruction loss. So you can think about it as measuring how good the Z is at reconstructing X on average over the different Z's. So I fix an, for every data point, I can ask sort of, if I push various Z's through my generative model, how well will I reconstruct my X? And I can look at this across different Z's and across different X's. And so that's one interpretation of what's going on in the first term, which is often why it's called a reconstruction loss. And the second term, you can think of as a regularization term because it's asking that this Q of Z given X is not far in distribution from the original P of Z, which is typically something simple like a Gaussian. So normally it's asking that whatever model you end up choosing, whatever your P of Z given X is, it ends up being close to some simple distribution. So you can think about this as a regularized optimization. In fact, you can analyze this as a regularized optimization problem. Okay, so the tricky part now is, well, how do we compute this KL regularization and actually optimize it? It turns out to not be that bad. So in particular, since everything is Gaussian, so this is to that earlier question about why Gaussian. Gaussians simplify your life a ton. So in particular, the KL divergence between Gaussians has a very simple form. It's easy to work out for yourself, or you can just look it up on, say, Wikipedia or Matrix Cookbook. The KL divergence between the neural network Gaussian and the prior Gaussian is going to look like this exact function. So this is sort of a nice convenient form, which is fully computable and sort of independent of any sampling. So this is 1 plus log of some function plus sort of the neural network sort of variance function plus minus the mean function. And if I average this out, I get the exact form of the KL divergence between your neural network approximator and the original Gaussian distribution. If I had other distributions that were not Gaussian, this will tend to be a lot more complex. So this is sort of nice and simple, and this gives us an easy way to compute what this KL term is. Okay, the other term we need to compute is this reconstruction loss term, which involves an integration. In practice, we can approximate this integration, since it's not a denominator, tends to be sort of efficiently approximated using sampling. So in practice, what we do is we sample a batch of data and use this batch of data as an approximation of this expectation. So if I give you a Q, which is this Gaussian distribution, I can sample a bunch of Z's from it. And based on those Z's, I can push them through the generator and get an approximation of this expectation. Okay, so I can put these together. Now I can compute this lower bound as a sum of this KL term, which we showed has a simple form as the sum of like means and variances of functions and things like that. And this empirical average as an approximation of the expectation. And so now we can try to optimize this when we are trying to fit the parameters in the E or the M step. Why does the KL divergence have nothing to do with P of Z? It does. Let me go back to the term. So most often, it's a great question actually, because I didn't discuss this well. Most often we use simple Gaussian distribution with mean 0 and covariance I identity as the latent distribution. If I make this more complex but still Gaussian, the form will be the same. There'll be an additive term for the mean and the variance of the latent distribution. The reason we don't use something more complex is something simple like a mean and variance, we imagine that the sort of forward neural network can handle pretty well. So there's no reason to add it to sort of the P of Z. You can imagine adding more complex structure. This came up in the last lecture when we were talking about, should I just use a single Gaussian? Should I use a mixture of Gaussians for P of Z or something more complicated? In practice, it may or may not be useful. The basic definition just uses a sort of simple standard Gaussian as the original P of Z. So because this has fixed parameters and we know what those parameters are, everything sort of, it looks like it doesn't show up, but it does actually, to answer your question. So it does because this particular form is exactly for a Gaussian when P of Z is this. If I change my P of Z to a different mean and variance, it'll have the same form, but it will have somewhat different parameters. The more important property here is actually the fact that we use a diagonal covariance, because that is what leads this sort of KR term to be a sum. Otherwise, it will be a much more complicated quantity involving traces and determinants and stuff like that. Traces anyway, traces and inverses. So it's a bit of a more complicated quantity. The P of Z term is again, by definition, we pick something like a sort of standard Gaussian, and then sort of everything else pushes through. Okay, hopefully that answers that question. Okay, so we've mostly solved our problem, not completely, but we're sort of partway there. So again, you can think about this as I'm going to get real data, which is my X. I'm going to push it through this function here, which is sort of Q of Z given X. And then it gives me samples from Z. I'm going to push that back through and get this log density. So this is P of X given Z, and end up back in. So this is the computation graph that I need to solve in order to compute this lower bound. And then we're going to end up optimizing this using SGD. Okay, so often we pick M to be small. It's actually quite common to just pick single sample. So in the forward pass, I sample a single Z. In the backward pass, I sort of do a update on the parameters based on the single Z that I sampled. But you can also do small batches and things work a little bit better. It doesn't seem to make a huge difference in practice to do very large batches. Okay, so there's one more issue. We're not completely done, but we're quite close to solving the problem. So as mentioned, this sort of reconstruction part requires sampling. And it turns out that you can't sample through you can't buff propagate through a sampling step. That turns out to be problematic. So again, in order to solve the full problem, I need to sample Z's. And that turns out to be a problem in the overall optimization. So as said, in the middle of our sort of having sampling at the beginning or end is fine. Having sampling in the middle is a problem. So the sampling in the middle causes a problem for backpropagation. So how do we backpropagate through a sampling step? So there's a way to do it. It's called, so for Gaussians, it ends up being easy. The key idea is we separate out the sampling and the computation. This has a name. It's called the reparameterization trick. What we do is we rewrite this sample of Z as a deterministic function and a stochastic function. And what is nice is that for Gaussians, I can always write a Gaussian, a parameterized Gaussian. So if I have a Gaussian Z drawn from sort of this with a mean mu and a variance sigma squared, I can always write it as first drawing epsilon from a Gaussian zero identity, and then stating the Z is equal to mu plus sigma times epsilon. So you might have seen this before. It's just sort of transformation of Gaussians between each other. So I can take one Gaussian and transform it to another. By multiplying by a variance and adding a mean, I get back the Gaussian with an arbitrary mean and covariance. So this allows me to go from identity Gaussian to a parameterized Gaussian very easily. And we're going to use that approach in solving this problem. So in particular, what's going to happen here is we have a Gaussian to sample from. And we need to do this in the backpropagation step. This is intractable. So we separate out the stochastic and non-stochastic parts of the problem, and we end up with a computation graph that looks like this. What is nice about this computation graph is that now we can backpropagate purely with deterministic quantities. So this Z is no longer needs, the sampling part of Z is fully described by this epsilon additional noise. So there is a path all the way from the X all the way back through the graph, computation graph, without having to hit sampling along the way. So this avoids this issue of backpropagating through stochastic or through sampling. So again, the idea is for Gaussians, I can separate out a Gaussian distribution into sampling from a Gaussian with no parameters and combining that with parameters. What is nice about this is what we care about are the set of parameters. So we can separate the problem so that when we're doing our gradient descent, the randomness doesn't show up as part of the gradient, as something that we have to do gradient through. So it's not part of the function graph. It can still show up as part of the problem, but it only shows up as sort of multiplying and adding things. It doesn't affect the, we don't need to do gradient through, so we don't need to have terms that look like d ZD parameter, where Z is a random, has a random variable parameterization directly. We can solve an equivalent problem by hiding the randomness. And the way we hide this randomness in a Gaussian is to separate the Gaussian into sort of a Gaussian that has no parameters and then adding and subtracting components. And this has a name, it's called the reparameterization trick. This is another case where it's easy for Gaussians. In principle, you can do it in other distributions, or you can do some approximation of it. It's quite a bit harder. So Gaussians are, again, special distributions where this reparameterization is easy, and this allows you then to sort of solve optimization problems through randomness. Okay, so now we've solved all our problems. We can now write the full lower bound. So the lower bound is a KL term as described. This KL term has no stochasticity in it. This is essentially the KL between our approximation distribution Q of Z and univariate standard Gaussian P of Z. And we have this loss term. This loss term has a randomness in it, but we separate out the random parts and the non-random parts so that everything is just can be computed without dealing with randomness within the computation path directly. So now the optimization process is as follows. I sample standard Gaussians, so sample noise. Based on that sample noise, I have, once I've sampled the noise and fixed the sampled noise, the rest of this is purely deterministic, so there's no randomness anywhere. As before, I sample a random noise and I sample a few samples of data from this. Once I sample both of those, again, I have a fully deterministic problem. And because it's fully deterministic, I can now write this down in a computation graph. I can compute the forward pass, I can compute the backward pass, and I can fully differentiate the whole thing with respect to components. The set of components are the forward components, which is the theta, which describes the generative model, and the backward components, which is the autoencoder, the encoder components, which describe the map from X back to Z. And so we can do this using sort of standard backpropagation from real data. Okay, so this allows us now to solve EM. It's not the full EM because we don't get the E step is not solved exactly. We do an approximation. And the M step, we also don't solve it exactly. We just take gradient steps to improve it. But in practice, we alternate just as before. So we alternate updating the Q parameters, which is our E step, and then updating the theta parameters, which is the M step. So together, this is stochastic variational EM. And this is, again, how we would fit this variational autoencoder model. Okay, so if I wanted to think about this in terms of sort of the components, this is what it looks like. Again, everything is deterministic apart from this component that is the sort of random noise. And because we've done this parameterization trick, we've separated it from the computation graph. So as you can see, there's a path all the way through the graph where epsilon comes as an input, but it's not in the critical path of any of the computation. Okay, so once we have this, we can then use standard backpropagation and use this to compute a variational autoencoder. Okay, so this is, again, quite popular. It's been used for lots of different problems. Here's examples of using this for something like the MNIST, which is this digit data set. Z, there was a question about Z earlier. So again, Z are latent variables representing degrees of freedom. So I can change the dimensionality of Z. So here's an example where Z is 2-dimensional, 5-dimensional, 10-dimensional, 20-dimensional. Very similar to what happened in PCA. Again, the key difference is in PCA, we had linear mappings. Here, we now have neural network mappings. So it can, in principle, it can describe more complex data distributions than what PCA can. What you'll find in practice is that VAEs tend to produce blurrier images than GANs as using the sort of standard approach as we've described it. Most current thinking, though it's not completely clear, I think it's more heuristics than sort of proof, but most current thinking attributes this sort of worse images, worse reconstructed images as a consequence of use of the reconstruction loss. Or in other words, this additive noise seems to make, because the additive noise ends up looking like a squared loss. Squared loss tends not to be very good for images. And so the intuition is that because we're using sort of the reconstruction loss that's a Gaussian, it ends up making our problem worse. So the extensions to this, to standard VAEs, for instance, to try to replace the squared loss with other kinds of losses, and there are cases where this can do a lot better. So in other words, replace the Gaussian at the end of the decoder with, so instead of having sort of sample Z and then add additive noise, you have some other distribution at the end of it, and that sometimes can do better. As mentioned, the whole process is a variational EM implementation. This ends up being a much better behaved loss function. So in terms of positives versus something like a GAN, VAEs tend not to suffer from mode collapse. The sort of KL divergence that you're minimizing all across the place tends to behave very badly if the distributions don't cover each other. I mentioned this briefly when there was a question about KL and sort of how it behaves. So if distributions don't cover each other, KL tends to behave badly. So in practice, mode collapse doesn't happen very often, unless there's sort of catastrophic failure of the whole training procedure. But whether this is a good trade-off compared to, say, sharpness in image applications depends on the problem. So it's kind of mixed. VAEs approximate the density in a way that GANs don't do as well. This density approximation can be useful in lots of different applications because it allows us to score things easily. We just showed that it allows us to implement maximum likelihood easily. VAEs learn both encoders and decoders. So VAEs learn mappings from X to Z and also Z to X. So data to latent space vector data. GAN only learns one direction and it learns Z to X, and the other neural network, all it's doing is scoring, so it actually doesn't learn a map back. I should say that there are other kinds of GAN models that do autoencoding, but a classic quote unquote GAN doesn't learn auto encoder and decoder. So this you can see of as a sort of advantage of VAEs, that you get both mappings. There's a bunch of current work using different kinds of probabilistic models. You can do VAEs and adversarial losses at the same time. You can do various kinds of conditioning and conditional generative models. There's a bunch of work trying to extend these ideas. Okay, so we have a minute, so I'll quickly go through the quiz. So some of the things that you should have learned from this, or you want to sort of remember when you go through your notes, is think about what the VAE objective is. And how it differs from what the GAN, both the generative model and the objective function are. So the VA objective being maximum likelihood and approximation of maximum likelihood, which ends up having this sort of regularization term plus a data fit term. The generative model being sort of additive noise or no additive noise. The approximations using variational autoencoders, the most important one is the variational approximation, where you replace computing the real P of Z given X with an approximation. The other important one is sometimes instead of expectations, we just use a few samples. Those are the two key approximations of variational autoencoders. And then the reparameterization trick is a way to remove randomness or stochastic sampling from the critical path of a sort of function graph. It's called a trick. It actually completely makes sense as a way to solve the optimization problem. But the way that you do it is that you rewrite the sort of the randomness as a sum of fully deterministic computation and some other component that is random. The key important thing is that no parameters, you don't need to you don't feed in parameters into the random function, which is what would break the gradient descent. So it ends up being tractable to solve. That particular notion will come up a bit later, actually, when we talk about reinforcement learning down the road. So it comes up actually all the time in machine learning. Okay, so the key components of the lecture today, EM, variational EM, and then using these for variational autoencoders. Next lecture, we'll talk about autoregressive models, which are sort of other models for sequence data. So we'll talk about recurrent neural networks, RNNs, LSTMs, GRUs, and stuff in that family. And with that, I am done with the lecture. I'll hang out for office hours. I'm going to stop recording in a second.